flare and substorm in space plasma. So you see, we have a satellite Hinode launch for observing the magnetic structure on our sun. And Tsuneta was the director who is working on this Hinode project. And they measure the magnetic field close to the sun. And 2008, the magnetic field structure of the sun was a kind of dipole field. On the other hand, in last year, they found it is quadrupole field, magnetic field structure. And this kind of dipole field is also the same mechanism like magnetic field in our Earth. So it is coming from dynamo action. So if we have some vertical magnetic field, because of the rotation of the sun, we have a winding up of the magnetic field and to strengthen the intensity of the magnetic field. And then because of the buoyancy of the magnetic field flux tube, we have a solar flare. And this number of dark spots of the sun has a period of something like 11 years or so. And then we had sometimes in the past so-called Maunder period, where we don't have any black spot, solar flare in the sun, where there was a very, very cold age, especially in Europe. And now, Tsuneta said, in 1812, there is the sign of the increasing the period of the dark spot. Okay. And interestingly, before the Maunder era, there was the indication of the increasing the period of sunspot. So that means Tsuneta told us that there might be a possibility to have more cold age coming in the near future. This is very interesting talk at the IPPC 12. This needs a clear understanding of the basic plasma physics out there. Okay. Then, interestingly, completely opposite discussion has been done by Professor Shibata of Kyoto University at this conference, saying that he is also a solar plasma physicist, okay, and leaders in Japan. And solar phase is associated with magnetic connection, and this releases the huge energy to the space. This is the reason why we have a solar wind. And the plasma in the magnetic flux is subject to magnetic buoyancy, and we have flux. If we have a flux tube inside on the surface of the sun, the pressure inside the magnetic flux tube becomes smaller than the outside because there is magnetic pressure over there. So the inside the flux tube, the pressure of the plasma becomes small. That means there is less particles inside the magnetic flux tube. That gives rise to the buoyancy to bring up against the gravitation of the sun. This is the reason why we have solar flare. Okay. Then Shibata said that sun is a not young star, and rotation speed is slow. However, he made a Kepler observation suggests there might be a super flare may occur in our sun. That is 1,000 times bigger than whatever we observed in the past. So he mentioned, from Kepler observation, here is the magnetic energy of the solar flare and the probability, and here is the size of the solar flare so far observed in our history. However, Kepler observation of the similar stars say that in our sun, we may observe this kind of big super flare. Okay? That is a very, very important observation, which is also published in Nature quite recently, I think last year. And this is a case of big so-called observation of the big flare. But even with this, below the observed solar flare, we have a geomagnetic substorm induced by this big flare. And geomagnetic storms result in the widespread blackout, especially in Canada. Okay. So we see aurora because of the big solar flare. However, this also have a strong effects on the human living, especially we are using electricity in 1 century or 2 centuries. That means this super flare may occur once in 5,000 years. That means if we continue to use this electricity for more than millennium, 1,000 years, we might see huge blackout covered all over the world. And all the airplane might lose the control. That's his prediction. Shibata predicted this kind of possibility we have. Okay? So that's the important topics in these days on plasma physics. And now I'm going to talk about the relativistic plasma physics, especially cosmology and plasma wave field acceleration. Okay. So this is Professor Tajima, who was in Texas, and he gives a very interesting talk in LPD, talking about plasma wave field acceleration. Maybe you don't know what is a wave field acceleration. In our sea, we see this kind of wave in the sea, but because of the nonlinearity of convective V nabla V, the wave in the large amplitude has a higher phase velocity, and to surpass the lower part and to have a wave break. Okay? This is a wave break phenomenon you see in the sea always. However, in the relativistic mechanics, this wave collapse will not happen. If we have a particle acceleration by the electrostatic potential, we have relativistic limitation of nonlinear physics. That means any particle cannot surpass the speed of light. That means due to this nonlinear process of the V nabla V convective acceleration, the particle will bounce at the speed of light. That gives rise to the very, very strong bunching of the particles, and then make a very, very strong electric field if you have a plasma. This can be created by the injection of electromagnetic field into the plasma. And electromagnetic field or laser electromagnetic field cannot have EZ, the electric field in the propagation direction. However, if it is inside the plasma, there is excitation of the plasma wave. That can have a EZ. And then very, very strong EZ can be created because of this laser wave field accumulation, wave field acceleration. That accelerates the particle very easily, 100 gigavolts per meter. So in LHC, there are large hadron colliders. There are huge, huge circle of ring accelerators. However, to get the gel energy or more. But their calculation shows that even 1 meter with this plasma wave field acceleration, we can create huge, huge acceleration. That he published in early days, and his paper is probably the largest citation, like 1,600 citation. On the other hand, in fusion, we have H-mode paper by Fritz Wagner, which has a citation of 7. But his citation is higher than the highest cited paper in the fusion community because of the interest from the elementary particle physics. Okay. I think you understand now on the plasma wave field acceleration. Another important recent development is the plasma cosmology, the kind of origin of the vorticity or magnetic field. Okay. So, in the universe, in our universe, we see many, many magnetic fields. So, for magnetic field, you know, it is coming from the, we can describe in a canonical momentum. Canonical momentum is velocity, momentum carried by particles and momentum carried by the field. Okay? So if we take the rotation, this is the vorticity. This becomes vorticity, and this becomes the magnetic field. So usually, you know, from the fluid mechanics, we know the vorticity conservation law, okay, in the fluid mechanics. And if we take the time derivative of the momentum, or you see this, we have a conservation of the vorticity because of the from this equation we can see that this term is exact differential, and that brings us the conservation of the vorticity in the flux tube. So in the non-relativistic mechanics, the vorticity will be conserved, including vorticity in electromagnetics is the vorticity of the fluid and also magnetic field. The summation should be conserved. Okay. However, Mahajan, this is Indian physicist, plasma physicist working on fusion, found that in relativistic mechanics, this vorticity conservation doesn't work because of the gamma factor of the relativistic factors. So the Wipro wrote a review modern physics in 2002 showing that why we we have so much magnetic field in our universe? Our universe must be the point during the Big Bang. It's very small, and there will be very small vorticity, generalized vorticity, including plasma vorticity plus magnetic field. So during the expansion to form our universe, why we have so much magnetic field in our universe? Then he provided some of the possible answer by solving this relativistic plasma physics, showing that in the case of relativistic plasma physics, because of this gamma factor, the vorticity is generalized vorticity will not be conserved. So that is the main reason why we have so much magnetic field in our universe. So this has been published in 2010, quite recent. So there are lots of very, very interesting physics questions related to plasma physics, as I mentioned. And that needs deep understanding of plasma physics. And, okay, then the plasma physics also has a good application in the technology. So we have welding, we use plasma. Okay. Copy machine, we are using same thing. Solar battery, fluorescent light, cancer treatment, plasma medical care, and medical tools, and surface coating, and industrial waste disposal, disinfectant, plasma propulsion, semiconductors, and fluorescent light. All are plasma-related technology. And PK2 in Hong Kong University, even plenary talk in ATPC, if you have your bone is broken, you have to cure the bone, and the magnesium metal is a candidate to bury, to connect the broken bone, right? And because magnesium alloy can be absorbed by the human body, and this is very suitable not to necessary to extract the magnesium alloy because it is absorbed by the body. However, he mentioned the absorption rate of the magnesium alloy is too fast to be cured, to be born, to be repaired. Then he coated using this plasma processing some metal different from magnesium alloy to have more longer time to be absorbed by the human body, to just fit to the repair of the body by the calcium. So he has many friends in medical professor to prepare which kind of medical tools they need. And he produced such a tools by the surface coating of the plasma. So not only semiconductors and copy machines and negative ion productions, there are lots of medical applications of the plasma. That is the situation for the widespreading application of the plasma field. So in summary, I would say, okay, or just 1 hour, okay? So plasma physics, as I say, becomes one of the fundamental disciplines for various physics fields. The huge range of interesting physics we can understand by using plasma physics. And recent development is quite significant, especially driven by fusion research. We developed, for example, gyrokinetic theory using lead transformation technique. That is now applied to the space plasma physics and also astrophysics. Astrophysics is now using a gyro kinetic simulation code to predict the precise behavior of the space plasma and the astroplasma physics. And I hope strong plasma physics course in FUDAN University, since this university is a Chinese leading university. And in addition, I would say you can download some books, 1,200 pages of book on fusion physics, edited by myself and German and Switzerland persons, and published from JAEA. It can be free download from this site. And I also published Physics and Fusion from Kyoto University Press. That has been translated into English, published from Springer, and also published in Chinese by Sichuan University peoples, translated, published from Science Publishers. And now I'm writing a new Springer book on frontier fusion research as an introduction to modern tokamak physics. It's based on my regular modern physics. And that's all. Thank you very much for coming and to hear my If you have any questions, please make them. He has some questions. Yes.
And I found that in your PPT files, you show some magnetic fields of the sun, and it changes very...
From dipole to quadrupole.
Yes.
Yeah.
Well, my question is there any experimental agreement with this measurements or...
I don't have a good idea that the measurements on the sun is still need more effort for the development of diagnostic technique. And we need a good simulation. And to make a good simulation, we have to understand what is the rotation profiles, what is the density range, and we need many things. And I don't hear any good numerical calculation of solar dynamo action. We know that the Kageyama made the Nature papers to talk about the mechanism of the dynamo action, self-generating magnetic field on our planet Earth. However, for the sun, we still have more room to have theoretical simulation contribution to agree with the experimental observation. So probably the many numerical simulation people in astroplasma physics is working on that change. And we know that our geomagnetism on our planet Earth have a change in the direction. That may be related to the same things on what happened on our sun. So that there is may have a change in the direction of the magnetic field polarization from this way to this way. Due to the unstable, if we have something happen in our outer core.
This change, how fast it would be?
Many years, things.
I have no idea. There is some historical observation on the change in the polarity of geomagnetic field. And we already know what is the period of the change. And we know that our geomagnetic field is reducing year by year. That's for sure. And we are going to have a zero magnet sphere in the near future, but maybe more than 1,000 years time scale.
Yes. And another further question is there any satellite which is working on the measurements of the magnetic fields of the sun?
Hinode is one of the Japanese mission machine,
Yes.
but I hope China should have such a satellite.
But I mean, it is measuring the magnetic field, or
Yeah,
I know by which method?
kind of. I don't quite know,
Okay.
but there is some technique
some
to
ways.
measure the magnetic field, and especially if in Tokamak we have a motional star effects to measure the orbital field.
Thank you.
That kind of things. I don't quite know the diagnostic system for the solar system.
So I want to give a little introduction of JAEA, of his work. Actually, why he asked this question, I guess it's because he's now doing some research on magnetic field-induced transition.
I see.
So with this kind of transition, if we have these light from the sun, possibly we can get the average magnetic field strength, but no orientation could be possible. So I guess that's why he asked this.
Very good question. You can talk to Tsuneta or Shibata. These professors are very, very prominent and leading present physicists in astrophysics, solar physics.
Thank you.
Other questions? We encourage a lot of questions.
Young students has so much huge opportunity for your future, and you have to take any opportunity to choose your way forward, right?
So when you're thinking, possibly you need time to think of your question. I have a question about the wave field acceleration. Because I think there are quite some people already doing the calculation for this wave field acceleration. Do you know any real application to accelerator, really?
Yeah. If you look at the Tajima's talk in NAPPC, most of the directors in the accelerator, like CERN and KK, and many of the Nobel Prize level physicists are quite interested. However, and from experimental point of view, there are still some big difficulties in having very strong laser power to make a laser wave field acceleration to be effective. And Tajima given talk on the laser, fiber laser acceleration. So to use huge number of fibers and to have a coherence between fibers, to have a strong, extremely strong laser light to make a wave field acceleration to be very effective. However, there was a question from the audience that 10, 20, you can match the phase of the fibers. However, if it is more than 100, how you can tune the phase of the fibers? That is the problem. But also, in UCLA, the Professor Chandrasekhar Joshi is the experimentalist who is doing very good job in the laser wave field acceleration, and have demonstrated a lot of laser wave field acceleration. which has been published many times in Nature and Science and Parallel. And I can give you a whole list of the references, and you can see from the web. Yeah.
Because I think in our institute there are several professors, theoreticians, and also doing.
Read the web illustration.
Yeah,
Good, very good.
that would be very helpful. I think all these
Yeah.
references.
And they are very friendly, although the Chanjoshi and Tajima is not quite in good situation. But both are very friendly with them.
That's good.
Yeah.
好，你们想好了有什么问题吗？得对到这个机会啊。So, when you are thinking, I have another question possibly. I will take the chance. What do you think is the biggest problem for realizing nuclear fusion?
Fusion.
Possibly there are many problems.
Yeah. One is the big project like ITER, because it needs so much money. We are doing the international collaboration. International collaboration is good, but takes so much money and human resources to communicate and to have negotiation. And I would think that the present cost of the ITER is the increasing cost of present ITER is coming largely from this international nature of the joint project. And if the China itself make the effort to make your own fusion facilities, the process will be quite simplified and can do more effectively. That's one point. That is one difficulty for fusion. The second difficulty is mostly with the plasma system is so complicated. We need a very, very strong person in physics who can understand everything. Each physicist is concentrating on one single physics, don't know other things. The integral view, who has an integral view, is very, very few people understand. And especially for the leaders in working in like a big project like ITER, do not understand fully on the plasma physics. That is another big issue. And the third issue is plasma Bohr interaction. Now, to create the high temperature plasma like a 10, 20 kV, 30 kV is easy. We now understand it's very easy to create such a high temperature plasma and high energy confinement time. But to solve the plasma Bohr interaction for the other energy producing system, we still don't have a good solution yet. So the plasma Bohr interaction for long pulse operation is the next challenge for the future. So in that sense, I'm very, very positive to have an academician one point to address the very, very long pulse operation in China with slightly reduced size than ITER, and to find out good solution for the diverters or plasma Bohr interaction to have a heat extraction and heat and particle extraction from fusion system. So there are, I said, three big issues.
Thank you. 我已经问了2个问题，不好意思再问了。你们想到什么问题了没有？不好意思啦。不过也没关系。假如说你们这会儿不好意思问的话，我们因为Professor Kikuchi 在这里还会有几天，他星期6走。我们想到什么问题的话，可以去找他。那么他在，因为我想我们这里在座的大概不光是现代物理所，是吧？那么， Professor Kikuchi 呢，他坐在那个现代物理所3号楼的202几啊，忘了。
204。
嗯？204。好，你们要是有问题的话，那么到时候再去问也可以。他基本上每天都在，他上课都是晚上上课，好吧？I guess it still need time to think or make you shy. So then I have told them your office.